In this chapter, okay, we begin our study on the unconstrained optimization, right? And the problem is expressed in expression 4.1. We minimize fx, where x is a vector in Rn space, okay? There is another form, okay, which this is an alternative form, how to express the unconstrained optimization. And here we emphasize minimization. Okay, if you have a maximization problem, then we can convert the maximum problem to maximization problem to minimization problem by using the fact that min fx is equal to minus max of fx. Okay. Um, in what are we doing in this chapter? Okay, in this chapter we will derive several optimality conditions for the optimization problem 4.1. Okay, and before we do that, there are certain definitions we need to know. Okay, and we will use these definition. Okay, so we will use these definitions through the proof this morning, right? And so here I show you, this is an example of okay, this in this pic. Okay, this is the in this figure I show you some, okay, the show the various type of local minimum. Okay, here in these two, you see that we have a word, a local minimum and a global minimum. There are, okay, so global minimum and local minimum. Also, we have strict minimum and unstrict minimum. Okay, strict. Okay, now let's look at the word strict and unstrict. What are they? Strict means that if we are in the vicinity of the local minimum, if there is only one minimum point in the neighborhood of okay, of the minimum, then this is strict minimum. So that means a strict means fx, okay, fx is greater than fx star. X star is a minimum, okay? X star is a minimum. Fx is greater than fx star for all x. for all x in the neighborhood of x star. Okay. If there is, and how about the non-strict? Non-strict mean that fx, okay, is greater than or equal fx star. We allow, okay, you see that we allow the inequality to be to have equate okay, the inequality is greater than or equal to, and this is why it's called non-strict. Okay, non-strict, sorry, not non-strict. Okay, now we look at the formal definition of local and global, right? Here, okay, here we consider a real function of n variables f, right? And then, okay, then we consider a function of n variable, a real function of n variable f, right? And then a given point x star in Rn, in the domain Rn, is said to be a local minimum of f if fx star is, okay, fx star is less than or equal to fx for all x in the neighborhood. This is how we describe the neighborhood. I think we describe the neighborhood in the form of the inequality. This is what we call is an open ball in Rn space. Open ball in Rn space. Okay, this is the norm. See that? Okay, if we this is the point x star. Okay, if we use the two norm, then I think is you see that it's clear. This is an open ball. Okay, it's a circular ball in the Rn space. If you use okay, if you use the two norm, this okay, an open ball with the radius epsilon. Okay, so any x, any point x inside this open ball satisfies, okay, satisfy the norm of x minus x star less than epsilon. Okay, normally the epsilon is very small real number. Okay, and so I think if we add the word strict together with the local minimum, then a point x star is said to be a strict local minimizer of the function f if fx star is less than fx for all x in the neighborhood. And in a similar fashion, we, oh no, and now here in definition 4.1.2, we, okay, the definition of global minimizer is given, right? Here you see that in a local minimum, we consider all x only in the neighborhood, whereas in the global minimum, we consider all point x in Rn space in the domain of minimization. Okay, is for all x in the domain of minimization. The domain where f, the function f, is defined. Okay, and okay, so here, okay, and if we add the word strict together with global, then a point x star is said to be a strict global minimizer of f if fx star is less than, okay, fx for all x such that x is not equal to f, x is not equal to x star. That means for other points in the Rn space. Okay, so that's the the definitions of minimizer, right? And then now we move to another. There is a you will find that in minimize, okay, in optimization, when the objective function f has a convex or concave property, then we find that many algorithms for solving optimization problems have some nice property, and the optimization problem is easier to solve than when the function f is neither convex nor concave. Okay, when the function f is not convex nor concave, then the optimization problem is called non-convex optimization. Okay, the nice property, one nice property of convex. Okay, when um, when all the function, okay, when all the when the objective function, let's say here I think here we only consider unconstrained, right? Unconstrained minimization. Okay, so when f is convex, okay, the problem mean fx x in Rn is called optimization problem. Yeah. Mm. And you will find later that a convex optimization problem, okay, in a convex optimization problem, the local minimum and the global minimums are identical. So that means any minimization, okay, any minimizer, okay, any minimizer is, okay, any local minimizer is a global minimizer of the problem. If, when the when the optimization problem is non-convex, then we may have many local minimums. Okay. Now now let's look at the definition of convex set and then convex function. Okay, before we define convex function, we have to define the convex set first. A subset of Rn S, a subset. Okay, S is a subset of Rn, and the subset S is said to be convex if for any 2 point x and y in the set S, the combination of alpha x plus 1 minus alpha y is also a point in the set S for all scalar alpha, okay, between 0 and 1. So a set S is said to be convex, right? If for any 2 point x and y in S, the condition 4.6 holds. Is true. Okay, 4.6 is true. Now let's see. So what is okay? When you look at the 4.6, when the term alpha x plus 1 minus alpha y, okay, this is called a convex combination. A convex combination of x and y. Okay? So once we define a convex combination of x and y, then we can restate the definition of convex set as a subset S in Rn is said to be convex if for any 2 point x and y belonging to the set S, a convex combination, okay, any convex combination of x and y are also okay, are also points in the subset S for all scalar alpha. Okay, for all scalar alpha between 0 and 1. Right. Now, what is the meaning of the convex combination of x and y here? When if you look at this, okay, we have to suppose this is the point x, right? And this is the point y in Rn space, right? The when you point x and y, okay, this is the vector x, this is the vector y, this is the reference point 0, okay? If you write, and so the alpha x plus 1 minus alpha y is a point on the straight line, okay, is alpha x plus 1 minus alpha y is a point that lies on the straight line connection between x and y. Can you see this? Mm-hmm. This is the Okay, from this you may not see that, but if you, I think moment, maybe I have to change this a little bit to the vector y and x in this figure. Okay, the minus, we find that the minus x plus 1 minus alpha y can be rewritten as y plus alpha x minus y. Okay, so if this is y and this is x, then the vector in green, okay, I'll use, okay, so this vector is, you can see that if this is the vector in blue color is x minus y, right? Am I right? Dollar, am I right? Yes. If this is x minus y, okay, then we multiply this with the alpha. And this portion is alpha multiplied with x minus y, right? Am I right? Alpha is between 0 and 1. Am I right? So
Yes.
what is this? Right. Okay, then what is this? Okay. So the green vector, this green vector, right? Okay. So the green vector here is the is equal to alpha x plus y minus alpha y, right? So now you can see that the, okay, here, now from this figure, then you can see the alpha x plus 1 minus alpha y, okay, which is called a convex combination of x and y, is a point lying on the straight line connection between the point x and y. Right, okay, that's the meaning of this. So that means, so what is a set, that means once we know this, then you can see that a convex set, okay, S is a convex set if for any given 2 points x and y in the subset S, then the straight line connection between the 2 points must be in the convex set S, right? So from this, then it's clear that now we have some example, right? A square is a convex on the plane xy on the plane in R2, then you can see that a square is a convex set, right? Or an ellipse is a convex set, right? If but this one is not convex. It's non-convex set. Why? Because given any 2 point x and y here, then you see the straight line connection is not, okay? Some part of the straight line connecting the 2 points, these 2 points are not in the set S.
Professor, which function would it be like this one, which would be the non-convex?
Oh, there are many. Now, no moment. This is the convex set. Oh, we define only convex set here. We have I haven't mentioned the convex function yet. Okay. Now we move to the definition 4.1.1.4.1. Okay, in which we define a convex function. Now, okay, a function f, which is defined on a convex set. Okay, a real function f defined on the convex set S is said to be convex if for any 2 points x and y in the domain S, then f of x, okay, f of a convex combination of x and y must be less than or equal to the convex combination of fx and fy for all alpha between 0 and 1. And if we add the word strict, okay, to the convex function, then a strictly convex function, okay, we change the sign less than or equal to be less than, to be a strict inequality. Okay, so this is the f of f of the convex combination x and y, whereas this is a convex combination of fx and fy. Okay, so how does a convex function look like? Then we see, okay, then we see this figure. The above figure illustrates how a convex function is look like when the domain is the real line R. Okay, if you plot the graph, then you see that when in the, okay, and when you plot the graph, this is a scalar function, scalar function. Then fx is the, okay, and here you have the fx and the coordinate x and fx, and this is where you have the y and coordinate the coordinate y and fy. Okay, then you see that the convex, the f of the f of the convex combination of, no, sorry, the function f of a convex combination of x and y uh this, right? So in this one, uh, the value of the function f at a convex combination of x and y for alpha between 0 and 1 lies under the straight line. Okay, like under the straight line. Yes. Okay. You see now in this one, you can see that an example of a convex function is fx is x squared or x to the power of 4. Right? Am I right? Hmm? Okay. And there are many. For example, in the R2 space, for the case of two variable, then a convex function fx is equal to x1 squared plus x2 squared. or fx is equal to x1 square x1 plus, I think, yes, one square plus x2 square. If we square it, then we still have a convex function. Okay. Well, to see that these are a convex function, then you have to prove, you have to show that the okay, you have to show by using the definition 4.1.4. Okay, and in a similar fashion, we can define a concave function. Okay, and we skip it because I think here we are interested in minimization problem. If we are okay, so in minimization, the function we are interested in a convex function, whereas in maximization, then that's the counterpart is the concave function. In a convex function, you see that here, and the function has only okay, either it's in this example, you can see that it has only one minimum point, right? It has only one minimum point, which is 0 in this case. Okay. Now we move to, okay. Now we move to the definition of the directional derivative. Why we have to see this? This is because, okay, I'll write it down. Yeah. In solving minimization, okay, that is so we search, or the algorithms move from one point to another. Okay, and for example, this is the xk is a current iterate. Then at this point in Rn space, then we make a move, okay, by we move along a direction which we will call it search direction sk. Okay, we move along this direction, okay, to find a suitable step size alpha, such that, okay, to find a suitable step size alpha, you will see this in chapter, okay, in chapter 5, right? Okay, here, okay, given a current iterate xk, then we will choose a search direction, or okay, or a search vector sk, and we move along that. Okay, we search along that that direction. Now you can see that the search problem in R-dimensional problem becomes a search problem in only one direction once the direction sk is given. Okay, so when we move along the direction sk, then we want to know what is the derivative of the objective function in that particular direction. So this is not derivative, or this is not derivative in the whole okay, in the Rn space, but this is a derivative only in one direction, and this is why we are interested in directional derivative. Okay, here we consider, okay, here we consider a real value function of n variables f. Okay, and then we write x as x naught plus lambda s. Okay, where x naught and s are vectors in Rn space, and alpha is a scalar. Or now here in this here it is a parameter in this case. A parameter, of course, it's a scalar. Okay. And the directional derivative of the function f in the direction s is defined by this. Here we use the Kato form, the Kato definition of derivative. Okay. The directional derivative of the function f in the direction s at the point x naught is defined as the limit of lambda approaches 0 of f x naught, f of x naught plus lambda s minus f x naught, okay, divided by lambda. Okay, so this is the and we used the subscript s of f x naught to denote the directional derivative of the function f in the direction s at the point x naught. Okay, and so what it is, then we will use the Taylor expansion. We will use the expansion to find what it is, because okay, what is the relationship, okay, of what is the relationship of directional derivative of the function f and the gradient vector and the search vectors. Now, to see this, then we use the Taylor series expansion up to the second term. So fx naught plus lambda s is equal to fx naught plus alpha s transpose gradient of f x naught plus 1 over 2 lambda square s transpose the gradient the H matrix of the function f at the point cosine of s, where cosine is a point between x and x, between x naught and x naught plus lambda s. Okay. Now you see that here, this is, you will see that in this case, the unknown cosine will vanish from the result. Okay. If when you see that here, this is the exact expansion. So you need to include the extra point, the cosine, into the expansion. Okay. If you use only x naught, that is not correct, because here in here you have to be very careful. You cannot write the mistake that people often make is that uh, they this is wrong. This is wrong, because here you use, okay, because when they are not equal, it needs to be you have to add higher order term as well. You need to add higher order term as well. So okay, so this is something just to remind you, because this is a very common mistake, a very common mistake people make in the analysis. And so from this, then we substitute f, the expansion, into the definition. Okay, into the definition. when you subs into the definition. So what we have, okay, I'll write it down. So here, fx of x naught plus lambda s, right, is equal to f naught plus alpha s transpose at fx naught plus 1 over 2 lambda square s transpose the Hessian matrix of f at the point assigned multiplied with s, with the vector s. Okay, then therefore the limit of lambda approaches 0 of f x naught plus lambda s minus f x naught divided by lambda is equal to the 1 of the lambda s transpose f x naught plus 1 over 2 lambda square s transpose f x naught, oh sorry, no, psi, divided by lambda. You see now the lambda here. We have one lambda here. This is lambda square, and this is lambda in the denominator, right? And then this becomes, okay, the then become S transpose square fx naught plus limit of lambda, because I think in the first term, lambda disappear, right? 1 over 2 lambda S transpose the Hessian of f the sine S. Now you can see that because we have one lambda here, then the okay, so the second term has the limit of lambda approaching 0, and this one vanish, right? Because it's multiplied with this one go to 0. The second term vanishes. Then therefore that we have the direct we have that the directional derivative of the function f in the direction of the direction s at the point x naught is in fact identical to S transpose the gradient of f at the point x naught. Right? Okay. So so this is the formula we use. So this is the formula we use to compute the directional derivative. Okay. So from here we know that the directional derivative of the function f in the direction s at the point x naught is the dot product between the search direction s and the gradient of the function f at the point x naught. Okay, this is the first thing that we know here. But then, okay, we see this further. Okay, now as I said, I think I'll rewrite this so that now we need to use this again, but I will rewrite it. Okay, I just rotate the figure. This is the point xk. Okay, if we move into this direction, is the vector sk. Okay, we move this. This is the alpha. Alpha is the, so this point is xk plus lambda sk, right? I think, okay, for the moment we skip the sub, okay? We just skip the subscription. Just say this is x naught, okay? This is the alpha is called a step length or step size. Because this is the alpha is the length that we move in the direction s.
Professor, then it should not be x naught plus alpha s.
Sorry,
It shouldn't be like x naught plus alpha s.
x naught plus alpha s. This is correct. Yes, yes, that's right. That's right. Yes. Did I say something wrong?
Actually, you wrote it like x naught plus lambda s. That's why I said it shouldn't be x naught plus alpha s.
No, it is x naught plus lambda s. Oh, sorry, this alpha. Sorry, this alpha. Sorry, yeah, yeah, I see. Sorry, just wrong. Yeah, yeah, yeah.
It's
Thank
okay.
you. Hmm? Okay. So in this, okay, once we move in one direction, then now you can see that okay, once x naught and s are given, then the point in if we move in this direction, then it becomes a one-dimensional problem. It becomes a one-dimensional problem. We use this many times. Okay, so okay, so this is f of x naught plus. So we can now you can write the graph of the function f versus the parameter lambda, right? Because x naught and s are given, are known. Then you see that when x naught and s are known, okay, f x naught plus lambda s becomes a function of a scalar variable lambda. Okay, when x naught and s are known, f of x naught plus lambda s becomes a function of one variable lambda here. Okay, and when you see this, so the slope at this point, I use the okay, the slope at this point. What is the slope at this point? Then you can see that the slope at this point is the directional derivative. This is the directional derivative, right? Am I right? Am I right? This is the directional derivative. F in direction S at the point x naught. Am I right? Am I right? And this is where 0. Am I right? You see the slope? This is the slope, okay? Now you see that this is the actually the slope at this point is the f d of f x naught plus lambda s by the lambda, where lambda is equal to 0. If you look at this, then you see if you apply the definition of derivative for in this case, you will see that that becomes, and this is actually it is equal to the definition of, equivalent to the definition of the directional derivative. Okay, now, okay, you will find later that we will, okay, apart from the slope at the point lambda is 0, then we are also interested to know the derivative of fx naught plus lambda s with respect to lambda for other values of lambda as well. Okay, so we define, so we define, okay, for convenience, then we defined phi of lambda as fx naught plus lambda s. Now you see that x naught and lambda and s are known, then the only variable is lambda. Okay, so we rewrite it. Then by using chain rule again, if you apply the chain rule in calculus, you can see that d phi by, okay, d phi by the lambda, this is equal to the s transpose, okay, the s transpose, uh, s transpose, the gradient of the function f at x naught plus lambda s. The point lambda here is, okay, the point here is, okay, this is the, this is lambda 1. So the point here is x naught plus lambda 1s, right? Mm. And if you have this one, this point, this is lambda 2, lambda is being lambda 2, then this point corresponds to another point here, which is the x naught plus lambda 2 s in Rn space. Okay, and the point x naught is correspond to the point lambda being 0 here. Okay, this is how we see this. Any question? Now, so here we can see that in directional derivative, then we know, okay, that now, and by using chain rule, we can see that now we can find not only the directional derivative of the function f, but also the derivative of fx naught plus lambda s, but with respect to lambda for other values of lambda as well. Okay, for example, this one, let's say at this point, okay, at the lambda 2, then the slope of the graph of the function at this point, okay, the slope, this one is equal s transpose the graph of f of x naught plus lambda to s. Okay, or we will use this quite a lot in chapter 5, in next chapter. Okay, but this is something you have to understand and remember. We will use this throughout the next chapter until the end of the lectures on unconstrained minimization. Okay. Okay, now we are ready to. Yes, I think we still have time. Although we may not be able to finish the whole chapter here, but I think at least we can cover some conditions. The first one, of course, here we establish three important theorems. Okay, the first one is called first order necessary condition theorem. Okay, here we consider necessary condition for optimality. Okay, so when we consider necessary condition for optimality, then we assume, okay, we want to see at the optimality what happens, what is the consequence of the optimality, right? The consequence of the optimality, let's say the optimality, when the optimality happens, it implies something, right? It implies something. So it implies something. Okay. If we use the logic, then we know that the negation of this condition implies that it's not optimality. The optimality doesn't happen. So, and this is why we call the condition in the box that this is a necessary condition for optimality. So what we do is okay, we now we suppose that f is a real value function of n variables, and the function f is continuously differentiable. And this is a pretty important assumption that we need to assume this, because when this happen, okay, you can guess when we need this assumption, then that means in the proof we will use the continuity of the function, right? Here we assume that x star is a local minimizer of f. Then what happens? Okay, then optimality. So what you see that here we replace this by up. X star is a minimizer. Okay. If X star is a minimizer, what are the condition in the box? Then if the condition in the box are not true, then X star, of course, is not a minimizer, right? Yeah, and this is why the condition in the box is called, this is a necessary condition. Okay, and this is, and you see when we use the word in optimization, if we use the word first order, it implies that we are dealing with the gradient of the function, f. Okay. Gradient or first derivative. Okay, and whereas the second order means it related to the second derivative, which is a Hessian matrix. Okay, and so x star is a local minimizer of f. Then we have the gradient of the function f at the point x star must be a zero vector. This is what we know in the theorem. So if x star, if the gradient of the function f at the point x star is not zero, then x star cannot be a local minimizer of the function f. You see, if you read the result in this way, you will see that the, the the gradient of the function f at the point x star being a zero vector is a necessary condition for the optimality. this is a necessary, the gradient of the function f at the point x star being a zero vector is a necessary condition for the point x star to be a local minimizer of the function f. Okay, now we can prove this. Okay, we will prove it. So here we assume, okay, in the proof we assume that x star is a local minimizer of the function f. Then what I think before we prove, you have to understand what's going on. When at the point x star, now start from the point x star. In the point x star, okay. So the point x star is a strict local minimizer. Okay. The point x star is a strict local minimizer. Okay, here we assume that x star is a strict local minimizer. Then if the point x star is a local minimizer, what happens? It means that any point in the neighborhood so that means and you say that we consider fx star must be less than, well, okay, if you no, it doesn't have to be local, it can be just a local minimizer. Fx star has to be less than or equal fx, right, for all x in the neighborhood at the point x star, right, in the neighborhood. Then so we represent the point x in the neighborhood. Okay, so x belonging to, okay, a point x in the neighborhood is is expressed as this one. Okay, is expressed as x equal x star plus lambda s, where for lambda is very small. Okay, and if this is the radius epsilon of the small, then you will see that lambda s, the norm of the lambda s must be less than epsilon. Okay, this is how we represent any x in the neighborhood as x star plus lambda s, where the norm of the lambda s must be less than epsilon, must be less than the epsilon. Now, if this now you can see that for any direction s, what happens? That means you see that for any direction s that we choose, if we choose the s in this direction, then what you see is that the graph will be like that. Am I right? Am I right, Emmanuel? Muhammad, am I right?
Suchin.
Am I right? If this is the direction s, then if x star is a local minimizer, then if we plot the graph of the fx naught plus this is the graph of fx naught. The graph of fx naught plus lambda s versus lambda, it has to look like that. This is where lambda is 0, right?
Yes, Suchin. This shows on the slope of the
And
function.
then if we choose the another direction, which is in green color, let's say we choose from well, from another, well, let's say if we choose any S. So for any S that we choose, the graph must look like this. Am I right? So the function f of x naught plus s is minimum at lambda being 0, right? For any direction s that we choose, you can choose any direction s. If x star is a local minimizer, then that means fx naught must be less than or equal to fx naught plus lambda s for any small lambda. Right? This is
Excuse me, Ajahn.
sorry.
Ajahn, the
Yes.
um the graph indicates the slope, which is fx naught plus lambda x all over lambda.
Yeah. It's
Yes, Ajahn.
of course,
So
but this is
for
the
this,
x naught and s are known. X naught
yes,
and
Ajahn.
s are given.
Yes, Ajahn.
So
Ajahn,
this,
what would be the shape of this graph if lambda is at 0?
and then from the moment I haven't finished. And then at this point, and then from the calculus of single variable, we know that at the minimum of fx naught, the minimum of fx naught plus lambda s, the slope at this point must be 0. Right? The slope at this point is 0 at lambda. Okay, so at this point is 0, right? This is the slope is 0, right? Mm. Am I right, Saran?
Yes, Ajahn.
Yes, this is okay. So now this is the, because this is, well, this is the minimum of a single variable that all of us get used to, right? Okay. Now, okay, once you understand this, then you say that this happens for all direction s that we choose. Then that means from this, then you can see and what is the slope, and you see that so you can see that the f by the lambda, that means, so that means the f x naught plus lambda s by the lambda at lambda is 0. This gradient must be 0, right? For any s in Rn space, right? The slope here, this slope is, this is the slope, right? This is the slope we are talking about. This is the slope. Okay. Then from just from this section, we see that actually this slope is actually the directional derivative. This slope is equal to, is in fact the directional derivative. Directional derivative. Directional derivative of f, okay, in s at x naught. And therefore, this is equal to what? This is equal to, therefore, we see that this is slope is equal to s transpose grad fx naught, right? this slope is equal to S transpose grad fx naught. Okay, so the condition that we have uh, now is that the S transpose grad fx naught must be 0 for any vector S, which is non-zero vector for any non for, and so this one is true. Okay, this is for any non-zero vector. So S here is a non-zero vector. Oh, non-zero vector, right? There is no point if we choose a zero vector. Okay, so if S transpose grad, when S transpose grad fx naught is 0 for any non-zero vector S, then what does it mean? It means that the gradient vector, sorry, this is the x, the point x star. No, sorry, this is the point x star. Sorry for the okay, x. This is the point x star. Okay. So we say that S transpose grad fx naught is 0 for any non-zero vector S is equivalent to the condition that the gradient vector at the point x star grad fx star, the gradient vector grad fx star must be 0 itself, and that's the end of the proof. From this, then we will use this. Okay, we will use this. From this theorem, we know that if the gradient at the point x star is not 0, then x star is not a local minimizer, and therefore the minimum will not happen at that point. So we look for another point until we find a point for which the gradient of the function f is 0 vector. Okay. And in the second one, I think this is all the time we have for today. Okay, and in the next week we will finish the other two theorems. Okay, to end this chapter. Okay, we will look at the second order conditions. We will look at second order necessary condition for optimality and second order sufficient conditions for optimality. Okay, this is you can read the slide before. Okay, before next lecture. And next week, if everything is okay, then we will move back to the classroom. Okay, next week. Okay, I'll.
To Professor, thank you.
Yes, I'll stop the recording first.